We are starting now. Welcome back, guys, to the second speech. And today we have Giovanni De Toni, which is a PhD student in computer science, both at Fondazione Bruno Kessler and the University of Trento. He's also a PhD student in the Alice project. And his PhD project is about counterfactual interventions and explainable AI. And he's also interested in algorithmic recurse. So Giovanni, please.
Thank you for the.
You can start.
The nice introduction. Okay, I suppose you can all hear me well from home, let's say. So, hello everybody. I'm Giovanni. Today I will mostly talk about, as my colleague said, algorithmic recourse and explainable counterfactual interventions. This presentation will be really high level, and I will just give you a, let's say, introduction on the field. I tried to place, for most of the things we'll say, let's say, links to the papers for the citations, so that if somebody of you is interested, then he can also have a look, more deeper look into these topics. Or if you want to just we can have some interaction after this talk, or maybe if you have some follow-up comments or questions, you can reach me by emails, or if you are more social on Twitter, you can see all my contacts here. So the best way to start into this topic, I guess, is to give an example. Okay, and so let's imagine that things Donald Duck, I suppose in Italian, in English, I think Paperino is the Italian name for this character. But as we all know, I suppose, this guy, let's say, is always penniless. Okay, it's our user. And let's imagine that he wants to get some money to make some presents for his nephews. So what he's going to do is going to basically go to a bank, which is our decision maker in this scenario, and he's going to ask for the bank for getting a loan. Okay. And in order to do so, he will give to the bank, let's say, a vector representation of his persona. And this vector representation contains several informations about maybe his age, his monthly income, his job, his education, and so on and so forth. The bank will use this information to decide if Donald Duck is eligible for getting a loan. And in order to do that, since we are in 2022, the bank is fully autonomous. So there are a few people as possible. And the bank will use, since it's really advanced, a machine learning model represented by a black box model that can be, let's say, a neural network that was pre-trained on previous, let's say, historical data, historical patterns to understand if somebody will be able to repay the loan once given. And the idea is that the bank gives this feeds the vector representation to the black box model, and the black box model will return a prediction or a decision, which is represented here by h of x. Obviously, this part is completely unknown to the user, in our case, Donald Duck. And from a certain point of view, is also unknown to the bank, because these black box model usually are, let's say, hard to inspect, and the decision function they learn, the discriminant function they learn, usually is not so easy to infer it by looking at the trained model. Let's imagine now that the decision given by this model is negative, which means the bank says to Donald Duck, unfortunately, we cannot give you the model, we cannot give you any loan, considering your historical patterns, your, let's say, feature representation. And that's the only feedback actually that the bank gives to our user, let's say. And since the bank itself cannot exactly know why the model says that Donald Duck cannot give, cannot get any, let's say, any loan. And therefore, this will make our user a bit angry, because usually what you want to know is, why did I get this bad decision, and what should I do to, be eligible for getting a loan? Okay, this example is a bit far-fetched. Usually, a normal bank wouldn't even dare to consider these kind of solutions. But in general, in the past years, we have seen that rise of the application of these decision-making systems to real-life, let's say, scenarios or applications. And one of them, for instance, I mean, there are many of them, both theoretical and also applied. For instance, one really famous one is the methods to predict the recidivism risk regarding convicted felons, I guess. And this part was made famous by the ProPublica investigations about the biases of the compass system, which is used in the US to understand if the probability of someone to reoffend once out of the jail. But then we have also a decision-making system, automatic, that deal with the university admissions. For instance, like here, University of Texas used to, let's say, admit students based on their probability of dropping out of college or the university after, let's say, 1 year. And then we have, let's say, also methods to rejecting or accepting job applicants, prescribed medication, and medical machine learning, etc., etc. And obviously, these decision systems are far from the optimal. And we've seen many news in the past years about hidden biases in these decision models, or even models that we thought that were, working really well in practice, but then in reality, the decision function they learned were completely biased or was based on the completely wrong factors. And therefore, this push us to understand better these machine learning models and to devise ways to, let's say, open the black box and understand what's going on the inside of these machine learning models. And in the past years, also this has become a, let's say, a requirement by the law. For instance, like in Europe, we have the GDPR, the let's say General Data Protection Regulation, that says that when there is an automated decision system that gives a decision to a user, what we want to have is the user must be able to understand why that decision was given, and, let's say, how to act in order to get a desired outcome. Let's say, how, in our example, what are the actions that Donald Duck has to do in order to get the loan. In the past years, we have seen, I think in the past like 5 to 10 years, we have seen a plethora of methods that can do, help us in this direction, which means they try to open the black box and explain our machine learning models. And here, I mean, this taxonomy is far from being correct, because some of these models let's say, division overlaps. But in general, there have been like many methods to do this. We have example-based explanations. We have model analysis explanation based on the feature importance, as SHAP or LIME. And we have also, let's say, saliency maps that understand, let's say, for computer vision, that shows us which are the area of an image that are, taken into consideration for making a prediction. And in general, also, there is also this line of research of, let's say, okay, we just discard the machine learning models we cannot understand, and we just use interpretable models such as decision trees, linear models, GLMs, etc., etc. But then this has, the issue that sometimes there is a trade-off between accuracy and explainability, which means that, let's say, the decision tree might be really explainable, but their accuracy on real-world data is maybe pretty low, because they cannot understand really well they cannot learn a good decision function. And there are this list is not exhaustive at all, but there are many surveys about this topic. Some of them are quite new, some other are outdated, but I mean, you can also find more if you look on Google Scholar or whatever. In general, all these methods are really nice, okay, but they fall short when they have to be used to explain to a user why they got a certain prediction or a certain decision instead of another one. Because, for instance, I can say to the user, okay, you got a bad decision, but you have to know that, let's say, your education and your monthly income are really important, and they determines your final decision. But these do not tell nothing about what were actually the factor that led that decision in the first place. And therefore, for the rest of this talk, we talk about counterfactual explanations, which I think are one of the methods to do explainable AI that is closer to be actually helpful to the user that is, who is affected by this decision-making system. Okay, so first of all, a little bit of introduction of, let's say, definitions. A counterfactual explanation is, let's say, a statement that says how the word would have had to be different for, let's say, a desirable outcome or prediction to happen. In the sense that these are, we do mostly in our life, we think in a, let's say, in a counterfactual settings, because we always think like, okay, if I had an umbrella today, I wouldn't have, I wouldn't have had to, dry my clothes because of the rains. And if we go back to our example with Donald Duck, let's imagine that the bank, instead of just giving to Donald this phrase like we cannot give you any loan, gives also to the user counterfactual examples, let's say X star, that says, okay, if you had this profile instead, like this user profile instead, then we would be able to give you the loan. And which means, okay, let's imagine that this X star represented the profile of a user that is eligible for getting a loan. And, however, we are not interested only in this, let's say, counterfactual explanation, but we are interested in the nearest counterfactual explanations, which means those explanations that are closer to the original user, that minimizes the changes that the user has to do in order to be eligible for this, for example, for the loan, etc. For instance, here we have this example. This graph shows the decision function of a neural network. The red one is, let's say, the good decision, while the blue one is the bad decision. And the idea is that, let's imagine that my user is the X here, and he has to move from this, let's say, unfavorable area to a more favorable one, which is like the red one. And here, A, C, and B, and D are, let's say, the counterfactual examples that says, okay, if you had this profile, then let's say here I would give you the loan. And as you can see, what we want is that we want to give to the user, let's say, either C, A, or B, or most probably A, even maybe A is like too close to the decision boundaries, but anyway, we want to give to the user C, A, or B as counterfactual explanation rather than D, because D is far away from the user in my, let's say, decision space. Okay, in like more theoretical term, let's imagine that what we're trying to do with the counterfactual explanation is the following. Let's imagine that we have a user which is defined by several features like x0 to xn, and this feature might be categorical, might be real, whatever, really. And what we have is a classifier H that takes one user from the user space and generates a decision. In this case, the decision is binary, so 0 and 1. But this setting scales naturally to a multi-class classification, so it's trivial to extend it. And the idea is that we have, let's say, a distance matrix that given to user describes how far they are apart in my, let's say, decision, like the user space. Okay. And when we do counterfactual explanation, what we want is to find the next star, which will be our counterfactual explanation, that minimize the distance between the counterfactual explanation and the original user, which is like this X here. Moreover, this new X star that I find must generate a different prediction from the original one. And in certain cases, the idea is that I need only to search for those counterfactual explanations that are in a certain feasible area. Because, for instance, I cannot say to the user, okay, if you were 10 years younger, I would be able to give you the loan, because it is something that the user cannot actually do. Basically, you help the user understand why he didn't get the loan, but you didn't give to the user any actionable information about how to actually overturn the bad decision he got. So, okay, this is like the more theoretical framework that most of the work of counterfactual explanation uses. Not all of them, but most of them. And in general, the counterfactual explanation have really nice properties. First of all, they are model agnostic. which means that usually you don't need to understand how the model is structured underneath. You just have to have, let's say, an API that tells you, okay, with this user you get the loan, or with this user you don't get the loan. Another property is that usually a counterfactual explanation is not, it does not come from the training data. It's something that you generate without the need to see the data from which the machine was trained, the model was trained. And moreover, they tend to be more human-friendly than the previous other examples like feature importance, sharp or lime, etc. Because they have both contrastive and selective, which means that contrastive means that they tell you in a counterfactual way what you should do in order to get the correct decision. And they're selective because they focus only on the specific attributes that you need to change in order to, let's say, overturn the decision of the machine learning model. And moreover, they tend to be relatively easy to find, which means that I need just to minimize the loss function, minimize the distance, okay? And I can just perturb my original user until I found a solution that satisfies, let's say, my needs, okay? Change the prediction, etc. And just to give you a brief example, this is the work, this is like the loss function used by this work of Watcher et al. That in 2017 first introduced in this concept, let's say, of counterfactual explanation. From what I know, maybe there are like much older works that use a different terminology than counterfactual explanation, but I'm not aware of them. But in general, what they did is like, okay, we have to minimize the loss functions. And imagine that X is my original user. X prime is the counterfactual we are trying to fit, to find, let's say. Epsilon prime is the decision we want to get. So imagine here is like get the loan. And lambda is a regularization parameter. The loss, what it's trying to do is trying to minimize first the distance from the desired model prediction. So this counterfactual must give me a decision which is close enough to this epsilon prime. Yes, lambda must be positive. Okay, so 0 to plus infinity. And then I have to minimize also like the distance between the original user and X prime, which is our counterfactual. In their work as a distance, they compute a distance feature by feature, okay, by considering also the median average of the, let's say, of the feature distribution. And they usually say, okay, X, Y prime, and lambda must be set in advance. And they also present a formulation in which they say, if you don't like this lambda parameter, let's say minimizing this means that you want to, this, let's say, absolute, like the distance between these two, these two values must be smaller than an epsilon. But I'm sorry, this is just for presentation purposes. And in the end, what they want to do is they say, okay, we want to find the counterfactual example, X prime, that minimize this loss. And also we are trying to also maximize the lambda parameter, which basically means, okay, we want to make this factor, the first factor, weight as much as possible in the decision, during my optimization. But also I have to minimize, which means I have to find a counterfactual that actually changes the prediction. But also this counterfactual must be close enough to the original instance. And this was one of the seminal work in this area. And obviously there are in the past years, like in the past 5 years, there have been many ways to generate counterfactual explanation by using, let's say, other machine learning models, reinforcement learning, evolutionary algorithms, and so on and so forth. Here we have like a list. We have, I don't know, like dice, face, maze, etc., etc. And for those of you who want to know more, there are many good surveys on the topic, for instance, like with et al., and which is a bit out, not out of date, but is like at least already 4 years old. And however, counterfactual explanation, let's say, are not the silver bullet for this explainability problem, because they have many issues too. As I showed before in the example of the nearest counterfactual explanation, many counterfactual explanations are possible given a single user, which means that there is this called a Rashomon effect. in which I have given a user many possible counterfactual explanations that I can give it to him. And therefore, now the problem is which one do I prefer over the others? Moreover, usually these counterfactual explanation, they do not present really any recommendation about how to get to that counterfactual scenario. Let's say maybe the bank can give to the user, okay, you should change these attributes in order to get the loan. But then the counterfactual example does not give any information about how to get to that, how to make that change. And moreover, most generally, let's say, going from counterfactual explanations to action is not exactly trivial, because maybe there are some features that cannot be converted to actions. And moreover, counterfactual explanation usually do not consider the feasibility or the user effort to change, let's say, the various features. So in the case of our, let's say, Donald Duck in our user, even if we give the counterfactual explanations, we do not exactly, the user might get confused more than, the user is not exactly helped by these counterfactual explanations. So the idea is like, now we want to move from these counterfactual explanation settings to, let's say, recourse setting, in which we give to the user instead some actionable feedback in order to get the counterfactual state needed to change the prediction. Okay, again, some definition first. The next step, okay, from moving from counterfactual explanation is to get algorithmic recourse, which is basically defined as a process that is able to reverse unfavorable decision made by automated decision-making system, starting from a counterfactual scenario. And in our case, we're going to use to move to counterfactual intervention instead. A counterfactual intervention, in this case, is not anymore an example of a user that actually gets a favorable prediction, but is actually a sequence of action that enables the user to go from his instance to a counterfactual instance that satisfies the decision. Moreover, each action has a cost, and this actually mimics the user effort to, let's say, change each one of these features. And the idea is that we want to minimize the cost of the complete counterfactual intervention by, and also given the previous constraint, which means that you have to be close enough, you have to be change the prediction of the model, and so on and so forth. And the idea that the counterfactual intervention also preserve all the qualities of the previous counterfactual explanations, which means that they are model agnostic, they are kind of easy to find, etc., etc. I mean, easy to find. It's oversimplification. So from a theoretical point of view, if we go from here, this was our previous definition. We keep only the definition of the user and of the classifier, and what we have now is that we have let's say a set of actions, and each action modify one of the features. We have a cost that take an action and let's say a user and return a positive number that should represent the effort that the user have to do in order to change the feature. And what we have now is that we, let's say, we have to find an intervention, a counterfactual intervention is I star, that minimizes the complete cost of each action. Let's imagine that a counterfactual intervention is a sequence of action, AI, going from 0 to t, such that, let's say, applying these interventions to the original state, x0, then produce a change in the prediction of the black box classifier. So again, given the Donald Duck example, we move from a simple counterfactual example to a more complete sequence of actions that the user has to follow in order to change the prediction. And obviously this will lead, be positively, usually is positively, let's say, perceived by the final user, the affected user. So, okay, this is seems to be really nice. Okay, a framework that is actually really useful. But then we have to. Let's take a little detour in the world of causality, because okay, let's imagine that the feature that the user have are the following: education, the job is the job, is income, is like if he has a house or not. And let's imagine that we have a DAG, a directed acyclic graph, that says how, let's say, that explain the causal relationship between the various features. For instance, my income is actually influenced by my education level and my job. And also, let's say, having a house or being or having having a rent contract depends on my income. And let's imagine that I have a series of actions that I can do. Let's get a degree, change the job, change the house, etc., etc., and that I want to generate an intervention by using these actions. With the causal graph, we can notice that the different permutation of these actions can generate actually, I mean, they enable me to get the same final state, but they actually have different costs. Because, for instance, if I want to buy a house, okay, maybe buying a house first is actually costlier than maybe doing it at the end of the sequence. Because, for instance, if I don't know, get a degree first, change a job and become, let's say, a manager, whatever, then these two actions will influence my income, and having a greater income, which will make it easier to get a new house, let's say. So in the end, when we generate a counterfactual intervention, we have to make sure that we need to take into account this kind of causal relationship in order to generate the minimum cost intervention. And recently, there was a paper that says that actually it is impossible to guarantee optimal recourse, which means to generate, let's say, the optimal intervention without accessing this kind of true causal graph that explain how the features like interact with each other. Again, in the past years anyway, moving aside from causality, there have been in the past, let's say, really recent years, like 3 years, there have been many new ways to generate counterfactual interventions with several techniques. And let's say we have like CSCF, which is like an evolutionary algorithm. We have SINT, which is based on reinforcement learning, and so on and so forth. And just to give you a brief, let's say, flavor on how it is done, I will focus on CSCF, which is a method to do counterfactual interventions with evolutionary algorithms. And as you can see, as we saw the previous theoretical definition, here they try to minimize, let's say S is my intervention, and what they try to minimize is basically multi-objective optimization problem with, they want to minimize the sequence cost, let's say the distance between the user and the counterfactual, and some other, values based on the feature that we want to change. And moreover, what they want to do, okay, we want to minimize this loss function, but we also want to be sure that the final counterfactual intervention must get an accept decision, and also to ensure feasibility, some constraints might be satisfied, has to be satisfied. And as we were talking about causality, they employ a causal, let's say, a causal setting to ensure to find the optimal intervention sequence. And they, as I said, they use this kind of evolutionary algorithm framework in order to generate a solution, which means that they have a genotype, which is a real vector, that it is then converted into a sequence of actions, which are basically action and the argument of the action. And I mean, it's nice work, and they show that they are able to actually produce interventions that are cheaper than original solutions that do not consider a causal graph. Like here, this is like the gain they have in on their solutions. Okay. However, even in this case, counterfactual interventions have the current methods have several limitations, and they're not either like the silver bullets for this problem. And the main one are like, let's say, they most of the techniques we have are optimization techniques, which means that they try, there is a learning component involved, but they usually, what you have to do is to run them ex novo for each user, which means that you have to solve an optimization problem for each new user that you want to provide algorithmic recourse for. And this might be a really costly process because you have to, let's say, maybe you have to send thousands of queries to the underlying black box classifier, which might be, I don't know, rate limited, or might be, you know, you have to pay, let's say, for make a query to this model. And moreover, one of the issue that is more important is that these counterfactual interventions fails to explain why the model suggested these actions in order to get the counterfactual and not something else. Okay. And then recent work says that these counterfactual interventions have inherent limitation. Going from counterfactual explanation to counterfactual interventions is has some theoretical limitations, but is not. For those interested to delve into this, then here's the paper. And just to do a bit of self-publicity, lately we have been developed, we have quite recently released a preprint with Andrea Passerini and Bruno Lepoli that try to solve some of these issues that I mentioned before. For instance, here, our model is based by using a reinforcement learning model that is able to interact with the, let's say, the environment to find the sequence of interventions. And what we do, we generate explainable counterfactual interventions. Here we have an example on the right, and let's say we basically generate a sequence of actions, okay? And for each actions, we give, let's say, Boolean explanations that says to the user, I suggest you to change education because your job is because of this, because you have, like, your job is this one and you have no education, so I want you to change, let's say, the education level you have. And the idea is that we also developed a more deterministic procedure in order to generate these, let's say, counterfactual interventions, given the, let's say, the pretrained model. And the idea is that this process do not require to interact with the underlying black box classifier. I can run this autonomously without checking with the without making queries to the black box classifier to generate it like this intervention. And you know, besides the various metrics of you know, accuracy, how the cost of this intervention, etc., is it was interesting to see that our models, which are basically the blue and these four here, okay, tend to learn to generate optimal interventions by making a lot of less queries to the let's say, underlying black box classifier. And here the competitor are like this green and orange, and the scale is logarithmic. And you can see that, for instance, here the green one makes thousands of queries to the classifier in order to, let's say, being able to answer, to provide intervention for a set of users, while our model in our case like generates far less queries, and in case of this gray one is basically uses zero query at all. Okay, we're almost done, and let's talk about a bit of future directions for this field. This was a really like broad introduction to the topic, to the problem, but generally what we've seen that there are still a lot of open issues, and the research is going on. And generally, the first things that we want to do is that we would like to find models that are able to learn the cost of the user and the causal graph given in a data-driven way, because nowadays what most people do is that they fix a causal graph that is hand-drawn by the experts, let's say, and you also define manually the cost for the user, while you would like to learn them in a data-driven way. And ideally, you would also like to get a model that is robust to hidden confounders of this causal graph. Maybe some factors that you cannot influence, but are there and influence the final decision. Moreover, another important part is define like more human-in-the-loop counterfactual intervention, in which the user is actually introduced into this intervention finding loop, because maybe the users might have some preferences that are not captured by the model, the graph, the causal graph, or the cost, and maybe interacting with the user make it easier to generate more personalized interventions. For instance, maybe a user does not want to change his, to change his job. So you could say, I don't want to change the job, but I want to get the loan anyway. So let's try to find an intervention that enables you to get the loan without changing the job. And lately, which is something a bit subtle, is that usually people do not differentiate between the model recommendation and the decision, the final decision. Because usually what we have is that we have a decision-making system that actually gives a recommendation to let's say, a policymaker, which is human. And then the human, based on this model recommendation, has to, let's say, take a decision on giving you the loan or not. And we, like, by giving an intervention, maybe we, for the model perspective, we actually satisfy the requirements for getting the loan. But from the human point of view, we're not satisfying those requirements. So we need to take into account also like this dichotomy, let's say. Okay, this was all for the trip, and thank you all for the attention. And if you have any question, I suppose that we can use like the Regia says that from the backstage it says to me that if you have questions, just write them into the chat so that somebody can read them, and we have it's easier like for everybody, let's say.
Okay, so there is a question. So by Stefano Teso, are there models, classes that are both expressive and for which counterfactuals can be generated tractably efficiently? Or is there a strong trade-off between expressivity and the efficiency of counterfactual explanation generation?
Okay, nice question. Okay, the idea is like most of the works kind of assume that the decision, let's say the decision boundaries or the decision function, the hyperplane learned by the model is kind of, I would say, smooth or convex, okay? So that it's kind of easy to traverse it in order to find easily a counterfactual that gets you the right decision, okay? Or in some way, the decision boundaries like on smooth, but there are cases in which maybe, especially with neural networks, in which the decision function is quite fuzzy. So, especially if the neural network overfits, let's say, on the training data, and then it would be hard to find a good counterfactual, or the counterfactual I get doesn't make any sense because the underlying model doesn't make any sense. So I think that the answer is as long as the model is trained, I mean any model, as long as the model you're using is trained in a sensible way, then you would be able to find the counterfactual easily, and this counterfactual intervention will also make sense. But if the underlying model is trained badly, then what you get is basically, there is like this garbage in, garbage out. If the underlying model is trained badly, then what you get is equally bad as counterfactual. I hope to have given an answer to this.
Yeah, he's happy with your answer. Thank you. I think we have another question from the audience.
Yes, I have a question.
Yes, thank you.
So, two questions actually. The first question on slide 18, you showed the search space, which
18 is terribly far away. Yes.
Oh, sorry. You showed the search space and 4 different points which are not close to the user.
Yes.
Here, and you explained that like point A or point B is closer to user than point D. So my question is, how would you measure this closeness? Because if you think about it as like the amount of contribution it has to the final decision is one thing, or the amount of changes the user has to do to reach it.
In a setting of a counterfactual explanation or counterfactual, let's say counterfactual explanation, this is measured, let's say, by, or you can define in the work by Watcher et al. Like here, they measure it. Let's say that they measure it as the, let's say, distance between each of the single feature of the user with respect to the counterfactual. And this also translates into the difficulty that the user have to do in order to move from, let's say, X to D. Because for instance, D, let's say, increase your salary of $100,000. Obviously, what you get is something really, you know, maybe really far away in your like distance space. While maybe you know, keeping the same salary, but maybe changing, let's say, okay, you just have to change job. Maybe it gives you, let's say, a shorter path from the bad decision area to the good decision area. So it's kind of the decision is both, can represent both the distance between each of the features, okay, but also it describe also the how much effort will the user need to change the feature.
Okay, so the features are not based on the assumption that they all have equal difficulty.
No, by placing a cost, you can say no. Changing the job is actually more difficult than, I don't know, increasing of €1 your salary or $1.
And because I saw that at the beginning for the concept of explanation, you mentioned Lime and other methods.
Yes.
In slide 55, you don't need to go there. I will explain what was there. You showed how you tried to come up with a causal structure that shows the contribution of each feature into the final decision.
Yes. So
my question is precisely there, because like these concepts of like attention rate, integrated gradient score, Lime, all of these techniques at the end of the day are doing the same thing. Even if you simply mask the feature and see the drop in the, I don't know, the confidence score or something like this, again, you are doing the same thing. What is the difference again?
The difference is that when Lime tells you from the model perspective, what are the most important features, while from, let's say, from the user point of view, what you have is maybe a different causal. Maybe for the user, the impact that you have when, like, from a cost-wise, if from the user point of view, maybe changing the job is much more, let's say, what happens is that when with Lyman and Schaap, I think, they give you the perspective of the model. The model thinks that these features are the most important, and these are the ones that, you know, are taken into account in the decision or weights more. But then with the causal graph, you want to model like kind of the user instead. Like for the user perspective, maybe let's say the features that are much more difficult to change are something else. Okay.
But the objective is to change the decision.
Exactly. Yes. But the point is that maybe since you see that there might be different possible counterfactual that you can get. Okay.
I see.
You want to find the counterfactual that minimizes the cost for the user. You don't care like which one you pick. You want to find the one that say, okay, A maybe minimize the cost for the user, while D is not minimizing that. And in order to find the optimal intervention for that user, you know the causal graph of the user, not of the model.
I see. Which eventually would result in changing the decision.
Exactly, which in the end, and also this enables you to discriminate between A, C, B, and D. By having this causal graph, you can say, okay, the user actually prefer A or B over C and D.
I see.
And the point is like, okay, now we are fixing that manually, but it would be interesting like to understand like the causal graph given the data, which is actually intractable in practice, but you can do it. There are approximations to do that.
Thank you.
I will ask a question. So I'm just curious if you know, if you know the order of the graph. What I mean is that in this simple example you show us, the one of the loan from the bank.
Yes.
I would expect that the causal graph is really huge. Like you can change the type of contract, you can change really a lot of stuff. And do you have any idea or any clue about the size, the number of nodes, and the number of links of the causal graph, and how it affects the performance? Like reducing the graph, increasing the graph?
What usually is people trying to do is saying, okay, let's imagine the user have like 10,000 features, that the model takes 10,000 features, and you want to constrain the possible action the user can do. For instance, maybe the user out of 10 features the user can modify only 5 of them, because maybe the other 5 are, let's say, maybe are protected attributes. Okay, let's say age, gender, sex, whatever, and then they cannot be changed. And also, so therefore, you reduce. Let's say you have always manageable size graphs, because it's you don't want the user to be able to change everything, because sometimes it's not possible. And sometimes also it's a way also to understand if a model is fair or not. Because if you say, okay, this model is not giving me the loan, and then I try to find the counterfactual interventions that try to get me the loan by, for instance, like not, let's say I constrain my set of actions, and I find out that I'm not able to find the counterfactual interventions that enable me to change the prediction given my state, which means that the model is actually taking decision based on other factors that are unchangeable from my perspective. And this might be a sign that the model underneath is actually unfair or is biased towards certain categories of people with respect to others. But in general, yes, to return to your question, the graphs usually are manageable size. I usually don't have like big structures, but with I don't know, I'm thinking about, let's say, 10, 20 nodes at most.
Thank you for your answer.
So about models that guide the interventions, are those based on Monte Carlo research? What would you?
It depends. Okay, in my case, in our case, in the work we've done, we use Monte Carlo research to evaluate all the possible, like here, there is like tiny orange. We're using Monte Carlo research to guide the search of these interventions, which is kind of like fast, okay? And the reinforcement learning agents like generates a policy to, let's say, explore only the most promising area of the search space. But in general, you can mostly do whatever you like. Like for instance, CSCF use evolutionary algorithm, which means that they use mostly, let's say, they have a vector here on the figure on the left. They have a real vector, and the real vector is, let's say, perturbed by using, I don't know, techniques coming from the evolution, let's say mutations, crossover with other individuals. And what they do is basically they explore the search space by generating large population of individuals with different features values, and then they make them mutate, they evaluate their fitness, they only take the best one, they made them together, and so on and so forth. And then they come up with, by doing this for many generations, they converge to the area of the search space in which there are like the best interventions. But really, you can do really anything, like you can do Bayesian, you can also do reinforcement learning, you can do, as long as you can explore the search space efficiently, there is no preferred technique. So it depends. For instance, like evolutionary algorithms are really expensive. They, for instance, needs to evaluate all the individuals in their population, and so this means that they have to ask 1,000 of queries to the underlying black box classifier. While with Monte Carlo research or reinforcement learning, you actually ask very less queries, and you also learn a model. While evolutionary algorithm, you just have to optimize it for every new user, and it cannot be used exactly online. Okay, if the user wants the answer immediately, if the problem is complex enough.
We have another question from the chat.
Yes.
Vanet Osmani is asking if you have any thoughts on how to learn the causal graph automatically.
Okay, so there is learning the causal graph. There is a paper by Locatello et al. In 2019 that says that doing it only data-driven is impossible because you have no way in the causality settings. Let's say the problem you have is that when you learn the graph, when you learn the graph, the problem usually you have is that given only the data, you know that there is maybe a link between education and job, but you cannot infer the direction of the arrow. You don't know if it is like the education that causes the job or the job that causes education. There are ways to do it, and recently I've read some. I'm not an expert on that area because I'm not exactly into causality, but the point is that what they're trying to do nowadays is that they try. Okay, we first learn, let's say, how each feature is let's say connected to each other, and what they do then they try to perturb, let's say, this, okay, one of the node of the graph, and let's say, and they try to see if the other connected component changes. For instance, if having, let's say, a model of the system that I'm not that I don't know how it is done, but I can, I can query this model. If I see that by changing the education, also the job changes, and by changing the job, the education remains fixed, then I can say, okay, the link here goes from the education to the job and not the other way around. But honestly, there are, I think, many techniques about that. And maybe the audience has other thoughts on this.
I just want to make an observation out of that. Also, I don't know if you can hear me. Also, you should have access to the intervention.
Yes,
so
yes.
Not only to the
exactly.
IID data, but
yes,
to see
yes.
how the intervention has been done in order to change the prediction.
Like the point to me that if you have only the data, as my colleague said, if you have only the data, then doing this is meh. You can do it approximately, but you cannot do it optimally.
I actually have a question. So when you generate like a sequence of action, the user has to undertake to change the decision of the black box algorithm or whatever. You said you mainly consider the cost for the user,
yes.
right? But do you actually try to also look at the efficiency of the action? Like meaning how much the action contributes towards actually changing the decider decision weighted by the cost, or do you just consider the difficulty for the user?
I just consider the difficulty by the user. The point being is that if you want to check, okay, I should change this because it's the model. I think that job is more important than the income. Let's say, then you would have need to access the let's say the black box model in some way to understand how it decided which is more important from the other. And usually this is not what you want to do because then the technique you have is not model agnostic anymore. For instance, like here, okay, Synth here by Ramakrishnan in 2020, they uses they do the optimization based thing to get the interventions. But what they do, they use the gradients of the underlying model, the black box classifier, to understand which is the most important features, and then they start changing those first. But then this model is not model agnostic anymore because you have to know the gradients for the model.
Sorry, if you query the model and see the contribution of each feature to the final decision, it is model agnostic.
No, because there are some models in which you don't have the gradients, for instance. It is specific to the model you have. Maybe you have like a neural network. Maybe you have a decision, I don't know, some kind of weird GLM or some other weird model that has no. The point is that you are making an assumption on the model underneath. Like the model, I need to have a model that can compute some kind of gradients on the features.
Not necessarily. It can be a binary decision. Like having a certain feature would result in decision as 0 or 1.
Ah, yes, okay, yes, sure. But then you end up with another problem that a bank will never tell you this. Because a bank doesn't want the user to know which are the features that are most important in their decision, because then you could do some kind of gaming thing, and theoretically you could manipulate the bank system in order to get the loan, even if you don't maybe add the requirements. So usually the bank want to have or whatever organization want their model to be, let's say, they give you only the decision 0 or 1. They don't give anything else, because otherwise you could be able to reverse engineer the policy that the bank uses for the decision.
So we go back to my first question, that the features are based on the assumption that they contribute equally to the system.
No, because you still have this black box classifier, and by querying the black box classifier, you can somehow, by going through the search space, okay, You will in the end converge to the solution that actually gives you the recourse, without knowing which feature. I mean, you can build in the end some kind of assumption of if you do enough query to the black box model, you can build, let's say, an assumption on which features are the most important for the decision, for the decision. But it's not something that you are allowed. That's why I was saying, okay, maybe the query, the API is rate limited. Because if you do enough query to their API, then you may be able anyway to reverse engineer the policy. So and they don't want it. They won't allow you to do it.
What we end up doing basically is to substitute or mask out a certain feature and to observe the change in the decision.
Yes, you can do it, but usually you don't. Okay, counterfactual intervention and explanation resembles a lot adversarial examples, because you want to do is you want to change some points in the features to get something else. But in that case, we want to fool the system. But in this case, it's like, no, we want just to get a certain prediction that is beneficial for the user. But we don't care
about the actual
what's going on underneath.
Thank you.
One question.
Okay.
In the definition of counterfactual explanation,
yes.
The definition of counterfactual explanation, actually, it's more or less of the same. The definition of adversarial example.
Yes, they are.
But adversarial examples are considered, let's say, security issues, for example, of neural networks or non-interpretable models.
Yes, but in this kind of settings, there must be counterfactual examples, because otherwise, you wouldn't be able to get a positive decision out of it.
Yeah, but someone could use counterfactual explanations actually to let's say, exploit the model in a, let's say, unwanted way due to the instability of the model.
Yes.
For example, with neural networks.
Exactly. Yes.
So, and there are a lot of adversarial examples. So it's really easy to get them. So it's really easy to get counterfactual explanations.
Exactly.
That's unwanted.
That's one of the concerns of these methods that usually I didn't put it in the slide, but it is one of the many that there still are, since the field is quite new. I mean, this field of explanation for the users, and the point is that since they are kind of adversarial example, you have problem with the privacy and the bank, because maybe the bank says, okay, you are probing my system. And what you're trying to do actually is to find a way to break my system to get maybe people to get the loan. Maybe you understand that my model, if you change a certain specific feature, then the model says, okay, that guy can have a loan. While if a human look at the feature of the guy, they would never give him a loan or her a loan. And the point is that why, let's say, in the action setting, when you define the action, usually this should be given, let's say, by. I mean, they must be decided, let's say, by not the bank, but you should decide certain actions and mask out certain features in such a way to try to find counterfactual explanation of examples that do not, let's say, exploit issues of the model. Let's say they try to reduce that, but it's not possible. Yes, in the end, it's not possible. But yeah, it's a problem. But is also a way for the bank to build a more robust model that do not have these kind of issues, or try at least to
yes,
because it's
I mean it's really more or less impossible to do this something at least neural networks without
yes, but they do it anyway every day, so nobody cares. That's there is this problem, but they work, so whatever.
They works because for example, in many cases you really a little bit of something, and you get
if the model is well done, okay. You have
in general. Sorry for the interruption, but in general, when you are referring to this kind of tasks, you are referring to tabular data sets.
Yeah, we usually mostly refer to data which are. Do you mean by tabular data? It's like what do you mean by? Yeah, I mean,
for example, I don't know, Excel stuff.
Like not images.
no,
When-
not
when
images.
it's
Ah, I
really
see.
easy to
Ah,
find that
yes,
result.
yes. Usually
Maybe-
there are.
Maybe I don't know, with tabular data, you can, it's more difficult to find adversarial examples, but I don't know.
It's not because of structure.
You have table in the sense that
That's
here
why also it's more difficult.
here there are like the age, the gender of the person. Maybe they shouldn't be there, but anyway. The income, the job, the education level, how much do they use their card every day, their FICO score if you are in the US, and other like thousands of features that maybe you want to have. And let's say only a part of them you will be able to modify, and these are basically why the action, you define the action. And then the idea is like, okay, the bank says that the user can actually really, maybe some feature actually cannot be changed by the user. Let's say, I don't know, there are maybe some feature computed internally by the bank, and the bank is like, okay, this feature is computed internally and the user cannot exactly change it. So that is not actionable, okay? And, but yeah, there are no images, they are tabular data mostly.
Okay. And maybe I think that, yes, but in the general setting, so but in adversarial examples are an issue. But in the practical, most practical cases, maybe they are not an issue. But let's say we can't actually do counterfactual explanations with images because they are
It's hard because in the images usually you change pixels, while here you change, let's say, concepts. In the image, you should to do something with the images. You should be like, okay, replace the legs of the cat with wings, and see what happens. That would be like counterfactual interventions for images, because changing a pixel does not give any meaning, while changing, let's say, your education level actually has a meaning.
Yeah.
You know? Okay.
Thank you.
Okay.
Okay, I guess.
So I think thank you, Giovanni, again for the amazing presentation. And now it's time to go have a drink
No,
together.
wait.
You want to
just
answer?
just a second, or we almost forget.
Yeah, we have a form. If you want to give, say, what's going good, what not, and also if you want to keep in contact with us, or we have also the YouTube channel now. So now we're having a drink together. You are welcome to join us in the Povo Center. And so for more questions, see you there.
See you there. Or like if somebody of you, like for the people that follow you from home, if you have any question, maybe follow up, whatever, you can reach me by email or email mostly. And yeah.
Thank you again.
Okay,